Professor Frank Armstrong again, First State University, going over some formulas for Management 370 Quality Operations course. Right now what we're going to try to do is try to figure out how to make an Xbar chart. What that means is we're going to take all the figures of all the parts that we've measured and we're going to crunch those numbers and try to develop control limits. Now remember, there's a difference between the tolerance or spec limits and the control limits. Again, in our example we showed previously, we showed that 1.25 plus or minus 0.005 was the tolerance limit. That means the customer wants it somewhere between 120 and 130. Okay? Now, the control limits, however, are a method that you devise using formulas to try to keep the product contained in a certain area well inside of the spec limits. So if your spec limits are out here, you want to try to control the product and keep it in there so there is no deviation, or so the product doesn't go out of control and therefore out of specification. So the whole purpose of this formula here is to try to devise control limits to control your process to make good product. So, a couple things you need to understand, and we're going to go to a chart here in a moment. We're doing problem number 11 in chapter 6. So, Xbar, that's two lines over the top. When you're taking, typically, when you're doing measurements of numbers for this type of an operation to chart your parts, you'll do 5 measurements of that part. You'll add the 5 together and you'll divide by 5 to get a mean value rather than accept the one value. So when we go to the chart that I'm going to be showing you here in a few moments, we took 20 sets of 5 parts, which means 100 parts, but 20 rounds of 5. So each time we take 5, we add the 5 up, divide by 5, and we come up with a mean figure. Once you have that mean figure, you add up all the means and divide by the number of means that you have, which in this case, we have 20 sets. So that means we would take the numbers we added up on all the means and divide by 20, and we get a mean average figure. So X bar is the average or mean of the mean values. R bar, range, is the number, again, just to remind you, the number that is different between the highest measurement in the set of 5 and the lowest measurement within that set. So if you have 5 parts that one of them measures 511, make that decimal 0.511, and the lowest figure that you have is 0.486, or excuse me, 0.481, then the difference between the highest and the lowest value would be the range, or in this case, 0.030. So, what you would do after you measure all 20 sets of the range, you would add up all the range parts, divide by 20, and that would be your R bar, or the average mean value of the range numbers achieved, okay? So, once you have those two numbers, you're ready to go to work. Xbar chart for the control limits is the upper control limit, that's the very top, nothing can go beyond that, is X bar plus A's of 2. In your textbook, on page 165 and 164, there's the formulas, and you look at how many measurements you have. So in this case, we had 20 measurements, and we want the A's of 2 number. So in this case, doing the math there, the number would be 0.58. So our A's of 2 was taken from that chart. We already know that our X bar number is 0.499, and we figured it out, and we know that our R bar number is 0.037. So to figure the upper control limit, we're going to take the X bar, that number, plus A's of 2 out of the textbook, which in this case is 0.58, times R bar, which is that number, and it gives us our answer. So, doing the math, we come up with 0.520, which is our upper control limit right there. And then the lower control limit is the same formula, except now you subtract here rather than add. So again, you've got X bar, which is that number, minus the A's of 2, which is still 0.58, times R bar, which is still 0.037, but you subtract that from 499, and you get 478. So our lower control limit is 0.478. So that means that we want to keep all the parts that we measure and process, manufacture, between 478 and 520. That's not the same as what the specification limits are that the customer was. This is to control the product so it doesn't go anywhere near those boundaries. Okay? Now for the R chart, to figure the range value, because you have to track the range, you don't want your parts going all over the place. It's the upper control limit equals the D's of 4, same page numbers in your textbook. You look at how many observations, and you go over and you find the number. D's of 4 times R bar. So in the book, D's of 4 is 2.11. R bar is still 0.037. So 2.11 times 0.037 gives us an upper control limit or range limit of 0.078. Now, there's a difference here. And this typically comes out this way. In the lower control limit, D's of 3, another chart. Actually, it's the same chart, but I mean a different column. We have 5 observations. As we mentioned, we're doing 5 measurements 20 times. There's a 0. That means D's of 3 is 0. Well, 0 times any number, regardless of what R bar is, 0 times any number is 0. So we have 0. That means that the lowest the range would be 0. Of course, you wouldn't have a minus 0. There'd be no such thing. So your range chart would be 0 here and should not have a range greater than 0.078. So the parts got to stay in between there. Okay? Okay, we're switching over to the chart now so that you can see those numbers and where we got them from, and hopefully explain a little bit better for you. These sample numbers are in your textbook, and again, this is problem number 11, but I'm going to put it up here just to help you and try and give you an idea of how these numbers were arrived. You probably can't see them real clear, but if you go to your book, you'll be able to figure that out. So again, we have 5 different parts that we've measured. We've took 5 parts and said that is sample number 1. We take the 5, and if you look at sample number 1 up at the top, if you can see it, it's 0.486, 0.499, 0.493, 0.511, and 0.481. Take those 5, add them together, divide by 5, and you have 0.494 for a mean. If you take the highest number, which is 0.511, and the lowest reading, which is 0.481, subtract that from each other, and you have a difference of 0.03, and that would be your range. You do that same thing for all 20 of your sets. Typically, 100 parts is what the industry requires that you measure. 105 sets of each, which gives us 20 different samples. After we get all those measurements, we figure out what the mean is of each set. We figure out what the range is of each set. We take the mean column and add all those up, 0.494, 0.509, and so on, and then get a total number, divide that by 20. Once we get that, we know then what our Xbar bar number is, and that was, in the problem that I showed you, 0.499. Then we take everything in the range column, we add those all up, we get a figure, and we divide that by 20. 20 because, again, we have 20 sets, and our R bar was 0.037. So that's how you get those numbers. Now you're going to take and make a chart so that you can see how your product is doing. You know where the center of the product is by doing the Xbar bar. So in this particular case, we know that Xbar bar was 0.499. So that will be the center line, and you see that up here on your chart at this point right here. That's your center line, 0.499, or your Xbar bar. Then your upper control limit are the broken dash lines and the lower dash lines. So we had an upper control limit of 0.528, I think it was, or 520, I can't remember, up at the top, and the lower spec limit down here of 0.427. So Everything that you plot needs to be within that area. Well, great, Frank, how do you plot? Simple. Remember that we figured out the mean for each set of 5. So for every set of 5 that you figured out the mean, you plot that number. So for number 1, that would be the first dot over in the far left. And then each set from there would get a dot, and you connect the dots, kind of like the old game you used to do when you were a kid doing the connect the dots. You connect it so you get a look of your run chart. And that is your X bar. Now, you do the same thing with a range chart, which is the lower end. And here you can see that we're plotting the mean of every figure. Of every set, rather. Lower control limit is 0. You can't go any lower than 0. The upper control limit was, I don't remember without the math, it was 0.078. So that would be 0.078. You plot the mean figure again, so your first set of 5, your second set, your third set, and so on, right on down the line, and then you connect the dots. As you can see, nothing went outside of the control limit, which means the process is running very good and is in control. So that's what that means. And again, this was problem number 11. Okay, I'm also going to post this and the chart of the numbers so that you can have them. They'll be attached in the video file where this file is going to be, so that you can look at that and watch this video at the same time. You'll be able to print it off, and hopefully it'll make more sense to you.